Hello everyone, this video is about complex conjugates and roots. Complex roots come in pairs of complex conjugates. A plus bi and a minus bi are complex conjugates. If a plus bi is a root, a minus bi must also be a root. The conjugate of z is z star. There are n roots of polynomials for polynomials of degree n. If the degree is odd, or if the order is odd, there is at least one real root, and if the order is even, we can have no real roots, or we can have pairs of real roots. For example, degree 2, this is a quadratic. You can use a quadratic equation, you get the usual solutions. You can factorize this as well. And another example here, almost exactly the same, but actually we get complex roots. We have a pair of complex roots. In this cubic polynomial here, we have one real root and two complex roots. The general strategies when finding roots or related to roots: given a complex root, the complex conjugate must be another root, and we can multiply complex conjugates to get a quadratic factor. So of course we multiply the factors and use long division to find the other factor or factors, and use rational root theorem and factor theorem to find and check the possible roots. So for example, fully factorize this quintic polynomial given 2 plus 3i is a root, complex root. Since 2 plus 3i is a root, 2 minus 3i must also be a root. 2 plus 3i and 2 minus 3i are roots, which means x minus 2 plus 3i is a factor, x minus 2 minus 3i is also a factor. If we multiply the two factors, x minus this, x minus that, we multiply, we get a quadratic factor. So we can multiply like this. We open up the brackets, the parentheses. We have x minus 2 minus 3i, x minus 2 plus 3i, and we can group the real part, x, not the real part actually, the part without I, x minus 2, x minus 2, and this is in the form of the difference of two squares. A minus b, a plus b becomes a squared minus b squared. So just x minus 2 all squared minus 3i all squared. X minus 2 all squared is x squared minus 4x plus 4. 3i all squared is 9i squared, and I squared is minus 1, so minus minus we get plus. 4 plus 9 is 13. So this is the final quadratic factor. If we know the quadratic factor, we can use long division to get the quotient or the other factors. So here if we do long division as usual, we get the quotient, which is a cubic polynomial. Now we can use rational root theorem to find the possible rational roots of this cubic polynomial. Remember the trailing coefficient divided by leading coefficient, factors of 41 only 1 and 41, factors of 1 only 1, so we have only 4 possibilities. And if you try minus 1, so you plug in minus 1, you replace the x with minus 1, remember factor theorem, actually you will get exactly 0, which means minus 1 is a root, and x minus the root, x minus minus 1 or x plus 1 is another factor. And now we know we have the quadratic and the x plus 1, and if you want to find the other factors, you can do long division one more time. So when you do the cubic, so this cubic divided by the new factor x plus 1, you will get the quadratic result here, quotient. And now you can try using the quadratic formula. So this is the quadratic formula here. And remember, we are trying to factorize here, actually not really solving. So remember, we have to multiply by a here. So ax squared plus bx plus c equals a times x minus x1 x minus x2, so minus not plus, and the x1 x2 are the roots or the solution to the quadratic formula here. So we plug in the b, the a, the c, and so on. We get the roots 4 plus minus 5i, which means it's also complex, a pair of complex roots, which means the fully factorized form would be the quadratic, the linear, and the quadratic. And if you're looking for the roots would be 2 plus 3i, 2 minus 3i, x plus 1, and 4 plus minus 5i. That's it. I'll see you again next time.